All right, let's get going. What is a mineral? And here we see a commodity dealer with his threefold subdivision of commodities: animal, vegetable, and mineral. That covers it. So, what is a mineral? Well, the definition of a mineral is a naturally occurring inorganic solid with a defined chemical composition, and it can vary. It doesn't have to be, there can be solid solution in that defined chemical composition, and an ordered atomic structure. So things like opal are technically not minerals because they don't have an ordered atomic structure. But we all know that minerals are the building blocks of rocks formed through geologic processes like volcanic activity, and minerals have characteristic physical properties like hardness, color, cleavage, which we can use to identify them. And then the next question is, how many minerals are there on Earth? And the International Mineralogical Association recognizes over 6,000 official mineral species as of last March. So there's a few. Now, this is something we need to keep in mind is we've been jumping around, mostly talking about elements and how they interact and solutions, and then elements combine to make minerals, and minerals combine to make rocks. So keep in mind these are different but related things. And then where we get this in, sometimes this intersection between elements, minerals, and rocks of interest, we have ores. So these are the rocks that we like, that we can make money on, containing certain minerals. These are called ores. So what's the difference between a metal and a mineral? It's basically everything. A mineral and a metal, their composition, form, how they occur in nature. A mineral is, as we said, naturally occurring inorganic solid, definite chemical composition and a crystalline structure, and it will contain metals depending on your definition of metals. But in general, a mineral is not pure metal. There's a few examples where, like native gold, mercury, few things like that. Even mercury is usually cinnabar, which is mercury sulfide. But here we got hematite. That's a mineral that contains iron, Fe2O3. And bauxite, that's the primary mineral source of aluminum. And quartz, SiO2. These are good examples of metals. I'm sorry, minerals. Metals, on the other hand, is a pure element, or it could be an alloy, a mixture of metals with specific metallic properties, such as shiny, conductive, malleable, etc. And metals are extracted, generally speaking, from minerals, ores, through processes like smelting or electrolysis. So, for example, iron, aluminum, and copper. Iron is generally extracted from hematite. Aluminum is generally extracted from bauxite, and copper is often extracted from chalcopyrite. So that's the relationship between metals and minerals. So how do minerals form on Earth? I can think of 7 ways. Crystallization from a magma, that's certainly one. Precipitation from a solution, that's certainly another. Metamorphism, you can form minerals that way. Hydrothermal processes, you could say that's related to precipitation from solution, but when I think of solution, I usually think of low temperatures, and hydrothermal processes are not. So biological processes, they certainly can make minerals. Certainly calcite or aragonite, as made by organisms, is well known, but birds and things make little magnetites in their brains. That's one of the ways they navigate. Volcanic activity, that can make minerals. And oxidation and reduction can change one mineral into a new mineral. So most of the rest of this class will be focusing on understanding how ore-forming minerals are created in nature. we've had a lot of basics leading up to this point. So I don't think we have time for this 14-minute video, so I'll just encourage you to take a look at it. It's basically Hazen has got a really interesting story about the evolution of minerals, that if you look at the number of minerals that existed on Earth, when it formed, it was much, much lower than it is today. That the evolution of Earth's atmosphere and biosphere has had a huge effect on making entirely new minerals, because it made entirely new pH and EH environments. So take a look at that. You can find that in the PowerPoint.
And so a key to understanding this evolution, and particularly the coevolution of Earth and life, is an emerging field called mineral evolution. This idea was introduced in 2008 in a paper that appeared in American Mineralogist. And I think of this as the very early part one of a three-part story about the evolution of mineral evolution. The earliest part was very qualitative. It was a story of the increasing diversity and the changing distribution of minerals at Earth's surface. And so you look at Earth and you see new chemical processes, new physical processes, and ultimately new biological processes that created new kinds of minerals. Now, I'm going to use the term mineral species tonight. And for some people, especially people in the biological sciences, that's a very odd concept, a species of mineral, but it has a very formal definition by the International Mineralogical Association. Every mineral has to be a naturally occurring solid. It has an idealized chemical composition like SiO2 for quartz. It also has an idealized crystal structure like the quartz structure. Every combination of chemistry and structure that's unique is a mineral species. There are about 6,000, I think as of this morning was 6,034 approved species, and about 100 new ones every year. So this is still a very dynamic, active field. So mineral evolution looks at several aspects of minerals: the changing diversity, that increasing diversity, the relative abundances of those minerals, the compositions then includes trace elements, minor elements, the isotopic composition. They tell us stories, and also the size and shape. And when you go to the museum, this incredible museum here just across the way, you see these beautiful crystal forms and the shapes and the colors. That's not part of the formal definition of a mineral species, and yet they're so important for us to understand the stories the minerals have to tell. So we're interested in all these. We think about the near surface, the upper 3 kilometers of the surface. That's where you can go down in mines, where you can see them and study them on Earth. It's also what we're most likely to find on other planets and moons, and it's where biology interacts directly with the rocks. And we'll see the biology is really important. So I have to make a comment about the word evolution. Right from the start, 2008, we got pushback on this, because the word evolution has several meanings. Now, the most basic general meaning of evolution is just change over time. And we know that happens. We see it around us. We see it in our own lives. Norman Bowen in 1928 talked about the evolution of the igneous rocks. And we talked about the evolution of stars and the evolution of planets and the evolution of meteorites and all sorts of things. It also, in our usage, implies increasing complexification or diversity or patterning. So an evolving system becomes, in a sense, more interesting through time. And there's a congruency, that is, each stage of mineral evolution or any other evolving system follows logically and builds on what came before. So it's a sequence, but it's not this. So erase it from your minds. Don't think about that. It's not Darwinian evolution. And as we'll see later on when I start talking about the missing law, there's something very special about minerals as an example of a much more general natural phenomenon of evolution. So here's the soundbite. If you need an elevator speech, new minerals form through a combination of chemical, physical, ultimately biological processes. And we can trace those changes through planetary history in 10 stages. So the 10 stages is a narrative starting very long time ago, more than 4.5 billion years, and going up, 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 in these stages that are somewhat overlapping and tell the story of Earth's evolution. The earliest stage is actually what we call stage 0, or the minerals, after meaning the original, the primary, the founding. And these are minerals that formed around stars long before our solar system. Stardust, if you will. These minerals form when an old star starts expanding its atmosphere, it gets cooler, and it's also rich in some of those mineral forming elements. So we see about 20 different minerals. We see about 12 different essential elements. When you combine those, you have the question of mineral evolution. How do you go from these stardust minerals, 20 minerals with 12 different elements? So what we see today, over 6,000 minerals with 72 different essential elements. That's the story of mineral evolution. And as I say, it takes place in 10 stages, the earliest ones being the condensates around that solar nebula. You can imagine something in space, a shock wave from an exploding star may have caused the initial perturbation, and a cloud of dust and gas began assembling, collapsing in, rotating. 99% of that material went to form the sun, which ignites, which sends out pulses of heat and melts the surrounding bits of dust into little droplets. They cool, they form igneous minerals. That's stage 1, 90 minerals or so. Those droplets condense into larger and larger bodies. And you can imagine this big and this big. First, it's electrostatics, but then gravity takes over. 10 kilometers, 50 kilometers, 100 kilometers. And when you get that large, the body starts melting internally from internal heat. And you separate out the metal to make a metal and iron nickel core. You have a silicate magma. You start making new minerals. You have aqueous alteration. You have thermal alteration. You have impacts that create new minerals. About 300 minerals in all. That's what we find in meteorites. That's what we think is probably, when you start forming planets, the endpoint for a dry world, like the moon, like Mercury. About 300 minerals, but it's difficult to imagine you get very much more. If you have a wet world, like early Earth, like early Mars, you can start doing new tricks. You can make clay minerals. You can make hydroxides. You can make ices at the cold poles. And so this gets us up to an estimated 450 minerals. That's stage 3. We think that may be the endpoint of Mars. Stage 4 is the formation of all those beautiful pegmatite minerals and granites. Granites form on Earth because you have a hot, big planet that's coated by basalt. And when you heat basalt from beneath, and it's wet, it melts, it partially melts. And that first melt is actually much richer in some elements like silicon and aluminum. And so you form this granitic melt. It comes up to the surface, it forms continents, and those continents are mineral rich, about 1,000 in all. So Earth has this trick. We don't know of any other planet in our solar system that could make pegmatites. But we do even more on Earth. We have plate tectonics. And that means you're recycling fluid rock interactions of not only the crust, but also the upper mantle, many, many millions of cubic kilometers of rock that's reworked. The fluids circulate, they concentrate elements, new kinds of magmas come up, new kinds of volcanoes form. You have ore deposits, these massive base metal deposits with sulfides, hundreds of salt-basalt minerals that never would have occurred before this point. You also have tectonic mountain building, which also creates high pressure, stressful environments where new minerals form, and also plate tectonics brings some of those high pressure minerals to the surface. So for the first time, you have all sorts of interesting high pressure minerals that never before graced the surface of our planet. And that's stage 5. And those first 5 stages give us about 3,000, maybe 3,500 or so minerals, purely physical and chemical processes. And that's it. We can't come up with any other mechanism that makes minerals. So how do you get to 6,000? And I've given you the punchline already if you've been paying attention. It's life. Life is an incredibly important component in the evolution of minerals. And that's kind of ironic because life could not have emerged without all the amazing things that minerals can do. They can catalyze reactions. They can actually serve as reactants, part of the chemicals that make life, templates, protection, scaffolds, all these different things. So here we have the situation where minerals play a critical role in the origin of life. life emerges, and then life plays a critical role in the origin of minerals. And this is the co-evolution of minerals and life that has taken place over 4 billion years of Earth history. Now, stage 6 makes these beautiful stromatolitic forms, makes banded iron formations, makes other kinds of things where microbes do a lot of the mineralization here. But we're not making a lot of new minerals. What the microbes do is they just speed up the formation of minerals that probably formed anyway. The game changer is when life learned how to use sunlight to break water apart and to release oxygen. That's photosynthesis, and that rise of oxygen in the atmosphere essentially rusted the planets, but not just iron. All different kinds of elements are sensitive to that presence of oxygen. And so, for example, copper minerals, at least 2/3, maybe more, of all the copper minerals known on Earth could not have formed before you had oxygen in the atmosphere. They're near surface secondary minerals, which are so beautiful in the collections of copper minerals, for example, at the museum across the way. But it's true also for all these other elements. They're called redox sensitive. They're sensitive to the presence of oxygen, and new minerals form at the surface by the thousands. So that's much of the Earth's mineral diversity. Stage 8 is a period of about 1 billion years in which the oceans, they were oxidized at the surface, where they were in direct contact with the atmosphere, but it took about 1 billion years for the oxygen to penetrate all the way to the bottom as it is today. And once you do that, then you get rid of all the ferrous iron, the reduced iron in the ocean. It forms those iron formations at the bottom of the ocean, and then you can start doing new things. It also caused great swings in the climate because suddenly the atmosphere changed, the climate changed. You had periods, cycles, where Earth became very cold, and by some models, it was covered with snow and ice from the poles all the way to the equator. And that means that the most abundant mineral on Earth by far was ice. Ice, yeah, ice. It's the H2O, that's the idealized formula in the ice crystal structure. So that's one of the 6,034 minerals. But then there are other times the climate got incredibly hot. It swung dramatically from icebox to hothouse, and ice may have gone completely extinct on Earth for some periods of time. And then when it gets cooler, ice comes back. So minerals can go extinct. They just don't necessarily go extinct forever. And then stage 10, this is when life learned to exploit minerals. When life came onto land, you had new soil forming processes with root systems. You also had all these different kinds of fascinating mineralization of shells and teeth and bones, minerals associated with the decay of organisms, minerals associated with coal measures. This is biomineralization. And I have to tell you a story. It's a secret. I know I said I love minerals, but I basically collect trilobites. Okay, so I've been collecting trilobites for a long time, and trilobite eyes have always fascinated me. This is the first trilobite that I ever collected. I was like 9 years old. It was from Silica, Ohio, and it just hooked me. The little eyes are, right now, they're made out of pyrite. The shell is cal. But the original trilobite eyes, those little lenses they're looking at you, originally were made of calcite, CaCO3. And they were single crystals of calcite with the C-axis pointing out at you. So if you can imagine, every one of those eyes was a calcite crystal with a C-axis. But there's a problem, because calcite makes a terrible lens. Red light and blue light bend differently. So everything is out of focus. What to do? Evolution always finds a way. It selects for the function. And in this case, if you just substitute radially different amounts of magnesium for calcium, you can correct for this chromatic aberration. And that's what the trilobite eyes do. They're incredible examples of nanoengineering. Every eye is radially zoned in calcium, magnesium to correct the bending of light so that they make a perfect eye. That's evolution. It always finds a way.
All right, so what are the ways to subdivide minerals? Well, number one is appearance, right? We can talk about metallic versus non-metallic. So for example, galena there, very shiny, lead sulfide, that looks metallic. And down there is a feldspar, which does not appear metallic. It looks vitreous. Metallic minerals are characterized by metal-like properties of high luster, like you see there on that shiny galena, conductivity, both thermal and electrical, and malleability. They're pretty easy to beat into shape, whereas non-metallic minerals have low luster, they're not nearly shiny, they're low conductivity, and low malleability. They tend to break up when you hammer them rather than flatten. Another way we subdivide minerals is by their symmetry, and this is something we're taught in our introductory mineralogy, petrology classes, the different crystal systems. Here we have them in order from their most to least symmetric. And in general, this classification system is not very useful for this class. We won't return to it again. It doesn't help us understand what we're trying to understand, but certainly that is a way that we subdivide minerals, is by their crystal symmetry. More useful for this class is to subdivide minerals into their 7 compositional classes. Number one is silicates, for example, olivine. The silicates all have Si as one of their anions. Oxides, for example, magnetite or hematite. We'll talk a lot about those things, especially when we get into the high EH environments. Sulfates, those will be talked about a lot, and sulfides will be talked about a lot, right? And there we're looking at a sort of an EH sequence from oxides, high EH, to sulfides, low EH. And we have carbonates, and then we also have native elements. There's not very many, diamond and gold. Those are ones. And then we have halides, where we have halogen as the anion, for example, fluoride. So those are the main major classes of minerals, and many ores are sulfides. So but then when they get up into the high oxygen fugassity environment, groundwater, you'll start getting some interesting oxides and sulfates and carbonates. All right, and then I think I guess I forgot phosphates before, right? Yeah, I forgot phosphates. So this one is repetition, but it includes phosphates. Monazite's a very important one because it has rare earths. All right, new minerals form as a result of exposure of original sulfides to oxygen-rich atmosphere, groundwater, and biological activity. So we've seen this diagram before, and we can see that the primary ore is probably a sulfide, right? So it'll be something like chalcopyrite, CuFeS2. And then as it gets closer to the surface, interacts with groundwater, oxygenation, and the sulfide breaks down and forms new minerals like malachite, is a copper carbonate hydroxide, and azurite. These are collector's items. People love their malachite and azurite. And then also there's this zone of secondary sulfide enrichment. So when a company is coming in to mine something, they're very well aware of this profile when we're dealing with sulfide ores, that you're not going to see the sulfides at the surface, unless it's a very recent exposure. You have to be aware that you're going to be seeing something else above the primary body. But these are all different minerals. So how to deal with so many, only 6,000 mineral names? Well, don't worry about memorizing names or formulas. just, write the formula after the name the first time it's used. So for example, we just talked about chalcopyrite, which is a very important one, CuFeS2. So you can remember it that way, but you're not going to be asked to remember minerals for the test. So how do we study minerals for our purposes? And microscopy is important. And here we need to talk about the fact that there are two types of microscopy, transmitted versus reflected. So transmitted light is we have our thin section here, and we have a light source down here, and the light passes through the very thin section and affects the light. And then we study that on this side. So that's a transmitted light, very good for non-metallic minerals and rocks. That's what we teach in petrology at UTD, and I suspect they teach that in petrology at Queen's University. Reflected light microscopy is different because these metallic minerals are opaque and they're better studied by reflecting light on them. So you have a light source up here, and it shines on the mineral, and then the mineral interacts with it and reflects it. And this is much more useful for economic geology. So we don't teach this at UTD, but Matt tells me they do teach it at Queen's University. So just to show you what that microscope looks like, here's a microscope. And it could be set up for either reflected light, right, where the microscope is looking down the specimen and light is being shined on its surface, or it could be transmitted light, where the light's coming up from the bottom through the thin section and then doing that, right? And those are both skills, both useful in petrology and economic geology. So let's just see an example of how we can identify pyrite.
Hi everyone, today I'm going to tell you how to identify pyrite in reflected light. So here is a pyrite crystal. It's fairly distinctive in that it is hard, so it'll take scratches really well, so it's often fairly scratched. Also, it's got a distinctive light yellow color to it. And you can see rotating the stage, it's just staying that constant same color. So it is not bireflected. So if it were bireflected, it would be changing color as we changed. Now we're putting in cross polars, so we can see whether it's anisotropic. So if it was anisotropic, we should be seeing the pyrite changing colors as we rotate the stage. And it's not doing so, it's staying black. Now sometimes it can be weakly anisotropic, but not in this case. All right, we're going to look at another sample, and this one has a few other minerals with you. So the bright yellow is chalcopyrite, and in the center there's a kind of pinkish one, and that's pyrrhotite. Again, we can see the pyrite isn't changing as we rotate the stage, and you might think that it looks like a little bit paler than the last one, but that's because it's next to the chalcopyrite. Now if we put it in cross polars, you can see that we have the pyrrhotite is actually coming in black to dark gray to black. That's what something would look like if it's anisotropic, which pyrrhotite is. One other thing to pay attention to is what we call relief. So you can see when we put it back into regular plain polarized light, that the pyrite seems to sit above the chalcopyrite, and that's because pyrite is quite a bit harder, so it's more resistant in the polishing. All right, this is our last example of pyrite. And one thing to bear in mind going forward is these are pretty pristine samples. So some of them are showing nice cubes. Mostly it's more kind of jagged edges, not perfect crystal form. But pyrite can have a lot of different crystal forms, but that's a subject for another video.
Okay, so there's lots of videos about that if you want to learn more about, reflected light microscopy and mineral identification. Now, understanding ore deposit formation requires understanding the paragenetic sequence. So paragenetic sequence is the relative order in which minerals form in an ore deposit. So what you can see here, these are all of the minerals that are in this sample, right? Quartz, epidote, cerussite, pyrite, all sorts of things. And you can see that by microscopic observations, whoever made this is breaking down the minerals into ones that formed early and ones that formed late. And that's just from textural relationships and reaction relationships. So understanding paragenetic sequence of an ore deposit helps geologists understand how that deposit formed, right? Whatever the first fluid was, it was capable of generating these minerals. And, with time, it wasn't. It generated other ones. And then in the supergene, once the air got and the groundwater got involved, then you see a different set of minerals being formed. All right, so another thing that we use to study ore deposits is fluid inclusions. So fluid inclusions are small. This one's very small. Looks like it's only 20 or 30 microns across. These things are normally less than a millimeter, but they're little containers of fluid that were trapped inside the crystals at the time of mineral formation. So if this is in a pyrite, you can say, if you can understand what the fluid that's in here, you've got some constraints on the fluid that formed the pyrite. So you can study these to reveal the nature of the mineralizing fluid and the temperatures that's occurred. So in this slide, we see 6 phases formed after entrapment of a single phase. And almost certainly when this thing was trapped, there was only one fluid, but that was at higher pressures and temperatures. And since then, everything's cooled off and you've got a bubble here, a vapor bubble. You can tell because it's round. And then there's a solid phase. I'm not sure what that is. Maybe here. This is solid phase 2. There's another one, solid phase 3, solid phase 4, solid phase 5, and then the remaining liquid. So we can obtain a minimum estimate for the entrapment by eating this up until only a single liquid phase remains. And this is a course in its own right, and we don't teach it either at UTD or at Queen's University. So I don't think that was a video. Was that a video? No. This one's a video. We're going to watch a 9-minute video called Fluid Inclusions.
Hello everyone, I am Sushil Kumar Putri. I would like to have a lecture on fluid inclusions. We will discuss about the basic principles of fluid inclusions and their applications in the study of crystallization history of different minerals. Let's know first what is a fluid inclusion. A fluid inclusion is a minor bubble of fluid that was trapped inside a crystal at some stage of its history. These are the paleofluids that was trapped either during the growth of the crystals or after the growth of the crystal by some of the imperfections or due to some deformations. And these fluids were trapped within some of the crystals. So accordingly, there will be different types of fluid inclusions that we will be studying. Well, based on the origin of the fluid inclusions, we can classify them into 3 categories. They are primary, pseudo-secondary, and secondary. The primary fluid inclusions are trapped during the growth of the crystals. So how we can know that these are trapped during the growth of the crystals? As we can see in this diagram, these are the primary fluid inclusions, and they are almost parallel to the edges of the crystals. So this gives us an evidence that these are trapped during the growth of the crystals. But the second ones, the pseudo-secondary fluid inclusions, are trapped along the fractures and some of the cracks formed during the growth of the crystals. We know that no crystal is perfectly created. There are some imperfection in most of the crystals. So due to these imperfections, there will be some cracks or some fractures along which some of the fluids can enter into the crystals, and they are entrapped within them. Uh, we can know that how these fluids are entered. So we can see in this diagram that they are not exactly parallel to the edges of the crystals, and they terminate along some of the crystal edges. So these are not exactly during the growth of the crystals, but nearly of the same as that of the primary fluid inclusions. And the last one, the secondary fluid inclusions, they are formed after the growth of the crystals. I mean, as you can see, these are the secondary fluid inclusions. These are formed along some of the cracks that were created after the growth of the crystals. Okay, so these are also known as transgranular fluid inclusions, and they are intruded along some of the cracks that are formed due to some deformation activities. But we will use only the primary fluid inclusions to study the crystallization history of different minerals, because these are actually formed during the growth of the crystals. Well, to study the basic principles of fluid inclusions, we have to take some assumptions that was proved before. So the first assumption is the inclusion fluid was trapped and sealed as a single homogeneous phase, that is proved by apparently same phase ratios. When we take some of the samples of fluid inclusions in the laboratory and heat them to a particular temperature, they are converted into a single phase. Either the, as we can see in this figure here, the vapor bubble is contracted with increase in temperature, and the total phase becomes liquid, because it is a liquid state entrapment. But when there is some vapors inside liquid, and with the increase in temperature, the size of the vapor increases and the total phase becomes vapor, that will be called as vapor state entrapment. In nature, the fluid is entrapped as a single phase, and with cooling they are converted into some vapor. But in the laboratory, when you do the reverse thing, I mean when we heat them, they are either converted into liquid or vapor, depending upon whether it's a liquid state entrapment or whether it's a vapor state entrapment. Well, the host mineral which hosts the fluid inclusions, there will be no change in the volume. The volume of the host will not change, but the volume of the fluids that were entrapped within that host, that might change with decrease or increase of temperature, but there will be no change in the volume of the cavity. Here cavity means to the host mineral in which the fluids are entrapped. When the fluids are entrapped within the cavity, there will be no exchange in the mass with the outside of the cavity. So we can call them as a closed system, and there will be some exchange of heat. So these are not exactly isolated, but they are called as a closed system. After sealing or entrapment of the fluid, there will be no change in mass, but there will be some exchange in heat with cooling of the mineral. Now the fourth one is we can know the origin of the inclusions by studying the petrography of the rock and the minerals in which the fluids are included, whether it's a primary fluid or it's a secondary or pseudo secondary. We can know that. So as we can discuss that in the second point, there is no change in volume. So we can say that there will be no effect of pressure, or whether there is some pressure but there is no effect of pressure. So we can call them as isochoric system. How we can say that? Because there is no change in volume. If there is no change in volume, so what will be the effect of pressure? Whatever may be the pressure, we can know them by studying the thermobarometry, but we can neglect also them. Now we will discuss about the mechanism of trapping for primary fluid inclusions. The primary fluid inclusions, they are trapped during the growth of the crystals. The crystals might be exactly planar surface, but they can also have some rough surfaces, because no crystal is perfectly developed. All the crystal have some imperfections, and some of the crystals might have rough surfaces and some have exactly planar surfaces. I mean, the surface can be smooth depending upon the cooling rate. And as we can see here, the the fluids in case of the well-grown crystals in this cube, the fluids come in contact with the edges of the fluid and some of the faces of the fluids, and it cannot easily intrude through them, but it comes in contact with the edges and the faces of the fluid. So these are most vulnerable to the fluid inclusions. But in the case of the fluids having rough surfaces, the fluids will be entrapped in the angular reentrants. As you can see, the yellow ones in these rough surfaces, the fluids are entrapped in the angular reentrants that captures the fluid. In these methods, the crystals can occupy some of the fluids, and fluid inclusion is mostly favored in case of crystal imperfections. So these are some of the important topics to be covered in this chapter, and if I am given the opportunity to cover it, I am very excited to do this job.
The 1 minute, 15-second video about heating a fluid inclusion to estimate its minimum temperature of entrapment. Okay, so the inclusion that gives you the temperature of when you get that homogenization of the fluid, and that gives you a constraint on the temperature of the mineralizing fluid. It's just a lower bound of temperature. Obviously, the temperature could have been higher, but it gives you some constraint.